Alrighty, so here on page 2 of our week 3 concept check, we have a pictorial representation of these orbitals, these spaces where electrons can be. And so this gives you a better idea. And again, it mirrors what we talked about in the lecture. And so here we have our 1s orbital, which is represented by this spherical shape. Again, this is a mathematically calculated area where up to 2 electrons can be, which I'm going to show as dots because I don't have room to show them as arrows, which we'll do later on in this packet. And so there is an S in every shell, right? There's a 2s, there's a 3s, there's a 4s. And so the only difference between those subshells, they all are spherical shape because they're all S subshell orbitals. But because they belong in different shells, their size is different, right? So remember that as you increase shell number, you're going to increase the size of your orbital. Now, notice that here we have 3 dumbbell-shaped spaces. These are the 2p subshell orbitals. And again, you can put 2 electrons in each. You could do it in either lobe. It doesn't matter, right? Remember, electrons are moving at the speed of light. And so the shaded and unshaded lobes represent an aspect that we're not going to get into in this class in terms of the amplitude of the wave function changing. Again, a little bit beyond what we're going to talk about. But notice there's no 1p because the first shell is so small. But after that, there's a set of p orbitals in every shell. So there's 3p and there's 4p. And then these 5 represent the 3d, and here we have these 5 representing the 4d. And so the d subshells are kind of cloverleaf, all except for this last one, which is the dz squared, which kind of has this p orbital with a kind of a disk or a toroid around the middle of it. But the idea is, again, you can put up to 2 electrons in each of these orbitals. And those orbitals, and again, it doesn't really matter which lobe you show them in. Those electrons, of course, aren't staying in one place. They're moving throughout that space at about the speed of light. And so these are areas based on the energy that we can calculate where those electrons most likely are. Another thing to keep in mind is whether you're talking the S or the P, if they're all in the same shell, they're all going to have the same size, right, in terms of the diameter. And keep in mind, right, we have one space and these are kind of nestled or nested inside this big sphere. Right? It's kind of like taking a giant stadium, and inside that stadium you have different tiers, different levels, different sections, different row numbers. That's what we're doing with electrons. And so we can give ourselves more and more information about where that electron's located. Now on the bottom of the page we have the same orbitals, but now I've arranged them in terms of energy. And so it turns out that the 1s is the least energetic, which means it's the most stable. And then comes the 2s, then the 2p, so we're moving farther out, we're becoming less stable or more energetic as those electrons get farther from the nucleus. Then we have the 3s, the 3p, and then here's where we have a little bit of an anomaly of nature, which is the 4s actually fills before the 3d. And notice they are very close in energy. And so this is just the way that it happens. It's also the reason why the D block on the periodic table, which we'll talk about here on the next page, is shifted down one, because we just find that the electrons fill into the 4s before the 3d. Then comes the 4p, then actually the 5s, and then the 4d. So there is a filling order. But keep in mind that in general, as you increase shell number, you're going to increase the energy of the orbital. It's going to be less stable. right? Those electrons, which are held into the atom by their attraction for the nucleus, that attraction gets weaker as that distance increases. Also keep in mind within a shell, the S subshell gets filled first because it's the lowest in energy. Then we fill the P, then we fill the D, then we would fill the F, which is the highest in energy. And again, right, not all shells have all of these. So in the second shell, the S fills before the P. In the third shell, the S fills before the P, before the D, there is no F, etc. And so just keep that in mind. All right, so that gives you a little bit more of a representation of what we're talking about. So now what we're going to do is move on to writing electron configurations and accounting for all the electrons in a particular element by placing them in these shells, subshells, and orbitals. As always, thank you for your time.